Okay, welcome to our first Stage 1 Physics Flipped lesson. The first topic we're going to look at is nuclear models and radioactivity, and the first subtopic we're going to look at is the nucleus. And in this video, part A, we're going to look at the structure of the atom, atomic symbols and isotopes. There'll also be a part B where we look at the forces that hold the nucleus together. I'll also start by just briefly explaining how these flip lessons will work and how you can best hopefully use the notes that will go with these flip lessons as well. Cheers. Okay, so the way that these flipped lessons are structured and the notes for these flip lessons, and as well as being able to access the videos for these lessons, you'll also be able to access copies of these notes, is that up usually in the top left hand corner in green we have the science understanding is what they're called in the SACE curriculum outline, but this is basically saying what SACE says you need to know. So that's our learning intention, and also often you'll see dot points, which basically describes the specific skills you need to be able to display, which is what we might call our success criteria. You might call other teachers hearing now. But really, you can use this up here as a bit of a checklist. This is what SACE says you need to learn in this course. And right through all these lessons, and therefore the flip lessons and the notes, you'll see this usually up here in the top left corner. And then we will address in detail what you need to know on the other side. So I think probably for most of you at this point, this is all fairly good common knowledge. And that is that atoms are made of protons, neutrons and electrons, and that we find protons and neutrons in the nucleus, which is the middle of the atom, and they are surrounded by shells of electrons. However, note, this diagram is not drawn to scale. Protons and neutrons are, well, we'll talk about this in the next slide, but protons and neutrons are of a similar size. Electrons are much, much smaller. And the atom is mostly empty space. So if you haven't already, go and look at this video here. And then what is also, I think, really important to know is how do we know this? How have we been able to develop this idea of what the structure of the atom is? And there is some questions on this, I think, in the book when you get to those. So I would also, if you haven't already, go and watch this video here. But up on Teams, I think I'd direct you to watch these two videos before you watch the flip lesson. So hopefully you've already watched those. And hopefully, to be honest, from your previous years, this sort of idea of what an atom is made of and what it looks like is not a new picture. So let's move on to learn a little bit more about the structure of the atom. So as I've already said, an atom is made of protons, neutrons and electrons. A proton has a positive charge, a neutron has no charge, an electron has a negative charge. Protons and neutrons are similar in size. An electron is about 1/2000th the size of a proton. So it's much, much, much smaller than a proton or a neutron. We find protons and neutrons in the nucleus, which is the center of the atom, and the electrons orbit the nucleus in fixed shells. Another word which may be new to you, but we use a little bit, is nucleons. And a nucleon is just a proton or a neutron. So anything that is in the nucleus, which is the protons and neutrons, is referred to as a nucleus. So, looking back here, can we describe the structure of an atom, including the relative size and location of the nucleons and the electrons? Hopefully, we can all confidently do that now. The next part we're going to move into is using atomic symbols, which is sort of described up here briefly, and I'll describe in more detail. And we have to be able to describe the structure of various nuclei, and where you see nuclei, various atoms is another word, from the symbol and vice versa. So, this is what the typical symbol we use for an atom. We have a letter which shows us what atom it is. So C is carbon. If we start from the start, H is hydrogen, He is helium, B is boron, Be is beryllium, and so on. So, down here, we often in physics at least, we put the atomic number. And the atomic number is the number of protons. So in a sense, it's a little bit redundant having an atomic number and a symbol, because if this is 6 protons, it must be carbon. If it's 7 protons, it must be nitrogen, therefore N. If it's 8 protons, it must be oxygen, therefore O, and so on. Up here, we have the mass number. And the mass number is equal to the number of neutrons plus the number of protons. So when we see a 13 here, and we know there are 7 neutrons, when we see a 13 here, and we know there are 6 protons, I've already said the answer, there must be 7 neutrons. 6 protons plus 7 neutrons equals 13 nucleons. If you like, that mass number is the number of nucleons. I suspect you've all seen this structure before. If not, it's pretty straightforward, and I don't think that should cause too much problem for you. What, if you haven't already, I would like you to do is just work through, go to this link, and I'll put the link up, or you can get the link from the notes, or I'll put the link up on Teams as well. And basically, in that link, you'll see 3 activities there. The atom, the symbol, and then some game activities. Just like you to have a work through those, just to get really, really familiar with this sort of notation and the structure of an atom and what we mean by atomic number, mass number, etc., etc. I don't think you'll find it too difficult, but there is some little bit of stuff in there in charge, which I haven't really covered, but I think if you've done some previously, you'll work it out. But if not, if you know about protons having a positive charge and electrons having a negative charge, you should be able to work out fairly easily. Thank you. So the next term we need to be really familiar with is isotopes. So what are isotopes, and how do we demonstrate and how do we show what various isotopes are? So isotopes of an element have the same number of protons but different numbers of neutrons. So I've got an example here. There's 3 isotopes of hydrogen. We can have hydrogen with 1 proton and no neutrons, so that's why the atomic number equals the mass number. There's only 1 proton. We can have hydrogen with 1 proton and 1 neutron, so therefore 1, 2, because 2, it's got 1 plus 1 is 2. That's known as also deuterium, if you've ever heard about deuterium, if you're into nuclear movies or watching The Simpsons or something like that. And then we can also get another isotope of hydrogen, which has 1 proton and 2 neutrons. So that gives it a mass number of 3. 1 plus 2 equals 3. That's known as tritium. When they're actually looking for evidence that someone like the North Koreans have launched or have exploded nuclear devices, they're often looking for tritium because it's one of the products often of those sort of reactions. So, isotopes, same element, same number of protons, same atomic number, but just different numbers of neutrons. Another one we deal with commonly is carbon. If you want, you can just pause the video and think about these for a sec. So these 3 isotopes, how many protons and how many neutrons. So if you want to pause the video now and just have a think about that and see if you can work out what they are. Okay, so hopefully it was pretty obvious that it's carbon and the atomic number is 6. So in every case, there would be 6 protons. However, in this case, the mass number is 12. So if we go 12 minus 6, that'll tell us the number of neutrons. So that would be 6. Here, 13 minus 6, it must have had 7 neutrons. It's like the example I had on the previous page. And this one here, carbon 14, would have 8 neutrons. So, hopefully that's fairly self-explanatory, and you may well have seen that in previous years. I would strongly encourage you, even if you are familiar with it, just for good practice, to go and have a look at this link here. Again, I'll put the link up in Teams. And initially just explore the isotopes activity. You'll see there's an isotopes and a mixtures activity that we'll get to in a sec. Just get you really familiar with this notation of how we signify basically what various isotopes are. Next, there's a couple of important things that we need to know about isotopes. Isotopes here, and we're talking about isotopes of an element, so these isotopes of hydrogen or these isotopes of carbon will have different physical properties. So physical properties is things that we can basically observe or measure, like density. And that's basically because the mass of the nucleus is different. Obviously, the mass of the nucleus of tritium here, hydrogen 3, is much greater than the mass of normal hydrogen 1. So that would make tritium heavier than normal hydrogen. However, isotopes have identical chemical properties. And by that we mean they react the same in chemical reactions. This will be more important in chemistry, but we do need to know this for both. You'll see here it says explain why isotopes of the same element are chemically identical but have different physical properties. And that reason the chemical properties are identical is because the number and structure of electrons on the outside of the atom is the same. And if you're an atom and you're reacting with other atoms, it's not really the nucleus that reacts, it's what's on the outside of the atoms. Atoms are very superficial. They're only interested in what's on the outside of things generally. So because the electron structure is the same, effectively they look the same to other atoms, so therefore they react in an identical way chemically. Another thing I just want to mention here, this isn't specifically mentioned in the subject outline up here, but it does cause a bit of confusion, and particularly for those people who do both chemistry and physics, is if we look at the periodic table, and if we've got a typical element here, say carbon, it will say the atomic mass here is 12.01. And that there is the average atomic mass for carbon. And essentially, and this is an approximation, but essentially if you've got a normal sample of carbon, 99% of it, roughly, will be what we call carbon 12, so it'll have 6 protons and 6 neutrons, and you'll have about 1% carbon 13, just roughly. So if you basically average those two out, the weight won't be exactly 12. It'll be just a little bit over 12 because there's some carbon 13 in there that's a little bit heavier. So that's what leads to the those atomic masses in the periodic table being slightly different from what we would call here is it's why it's not 12. Carbon 12 is the most common isotope, but there is also some carbon 13 naturally occurring. So if you've got a sample of carbon, it will have a bit of both in it. So overall, the mass of it will be slightly heavier. Explore that mixtures activity in that link up above here, and that'll give you a little bit more of an idea on that. Again, it's not super important to this course, but I think it is worth understanding, and it will help other things fall into place later on as we go. Okay, thank you.